Getting to fault-tolerant quantum computing requires improving qubit quality. The dream of engineers is the 4 nines, or 99.99% fidelity. Quantinuum, well known for its H1 trapped ion system, has found a way to achieve this elusive goal by switching from ytterbium to barium-137. Find out more about the state-of-the-art in trapped ion qubits in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. As you may have heard, late in 2021, Honeywell Quantum Solutions, who we've had on the show, has merged with Cambridge Quantum to create Quantinuum. Our guest today is an advanced physicist at Quantinuum, Tony Ransford. Welcome to the Post-Quantum World.
Hi, how's it going?
Yeah. I'm really excited to have you on because some potentially game-changing work you've been doing. As we covered last time Honeywell was on, the H series of machines use ytterbium atoms to create trapped ions. Can you tell us a little bit about the limitations or challenges that approach leads to?
Yeah, so ytterbium has sort of been the staple. Many people use ytterbium in academia and in industry for trapped ion qubits, but they do have downsides. Probably the biggest one is that the lasers used to control and do the gates are in the ultraviolet spectrum, and so these are challenging lasers for a lot of reasons, and they're not really compatible with industry technology, laser technology that's available and cheap and robust. And so the ideal thing you would want is some visible or infrared, so we can leverage telecom equipment. And that's one of the challenges of ytterbium, along with the fidelity that you can measure the ytterbium qubits at. It turns out that at least with the standard method for measuring ytterbium, the fidelities are low, comparable to where we want to be. Maybe not comparable to where we are right now, but the fidelities, the best done is sort of in the just over 3 nines, 99.9%. Fidelity is sort of the best ever done in ytterbium. So while it's been a great qubit and worked for many academic and industry, it does have its limitations.
Yeah, and we're trying to get to 4 nines, right? That's the idea. So this led you to work with, I guess, barium ions, which I guess could be cheaper, and if you use the wrong ones, maybe dangerous. If you want to talk a little bit about that.
Yeah, so I actually was at UCLA before I came here, and that was sort of the first place to use radioactive barium ions. 133 is the isotope you want to use for quantum computing that's radioactive. There's a lot of downsides to using radioactive barium, maybe even less obvious than just the radiation safety. Actually getting lots of atoms out quickly, and just the way that what we call loading, where you try and get the material into the ion trap to create the qubits, can be quite challenging with radioactive qubits. However, the structure is sort of optimal with the radioactive ones. So the real challenge we had was taking another look at the sort of the atoms that nature gave us that weren't radioactive and figuring out how to use them in order to make good qubits out of them.
Yeah, so that brought you to, I guess, barium-137.
Yeah, that's right. It has it has a nuclear spin of 3 halves, which is the radioactive version has 1 half, and that extra nuclear spin in barium-137 causes some issues. It creates more levels that you have to deal with. And we had to come up with techniques basically to deal with all these other levels in order to prepare the qubit in a pure quantum state, which is the initial goal. And so that was one of the challenges we had to overcome.
But in the end, you were able to use more standard visible green lasers, right? With 130.
Yeah, that's right. So 137 just inherently has visible colors, which is sort of why we chose barium. That's what makes the atom attractive. But I think initially it seemed hard to prepare this pure quantum state, but we were able to use these visible lasers to really prepare a pure quantum state.
And then, of course, the big news that was announced was the 4 nines, so 99.9904. And that's a measurement of span fidelity. So did you just want to explain that to our listeners?
So SPAM stands for state preparation and measurement. And historically, SPAM fidelities for any qubits have sort of hovered around a little above the 99.9x, so a little more than 3 nines. Whether it be ytterbium or even barium 133 or previous ions. And so with barium, it's really the measurement comes for free, whereas in ytterbium, the measurement is the challenging thing. And so barium, it's quite easy to measure, but preparing it's hard, especially 137. And so for the SPAM, you really just have to address all of these states with lasers and sort of what we call optical pumping, but prepare them into a single state. And this is what we call our qubit 0. And then you have to be able to measure. And the way we do that is our qubit 0, the ion doesn't light up. It glows like a star when we shine the laser on it. And when we're in the 0 state, it's dark and there's no star. And then when we put it in the 1 state, it lights up, and that is the star. And so we differentiating these two things and how well we can do it is what SPAM is, basically how well we can tell we've made a 0 or a 1, and how well we can actually make the 0 and make the 1.
Okay. Yeah, and also it creates quite an image in the mind of the listener, I think. I always look for scientific moments like that where it's like, oh, that's something you can very easily visualize. And all this comes from the DiVincenzo criteria for making a quantum computer, right? So there were the 5 for the machine and then the 2 for communication. So SPAM was 2 of those, the state preparation and the measurement.
Yeah, I think creating a fiducial state is one, and being able to measure that state out. And so that's exactly what we're doing. Where you can think of it kind of as the end of the calculators, the inputs, and the thing you read at the end.
Mm-hmm. And of course, somewhere in the middle there, you have to have gates. And has any work been done yet on getting these barium 137 qubits to actually gate with each other?
Yeah, that we're actively working on that right now. We have technology development efforts looking into gating of barium 137 qubits, as well as looking to transport. There's a handful of other things you have to make sure work before you build a quantum computer out of them. Mm-hmm. But getting the SPAM was maybe the one thing that was the most uncertain in our minds, at least. And so getting that out of the way really opened the floodgates to move forward. And again, now we're going to be doing gates on barium, but we're going to be using sort of commercially available technology and these very nice lasers that should help us push the actual gate fidelity better, not just the SPAM fidelity.
And will this give us any other benefits? Like, do you anticipate being able to control more of these ions compared to ytterbium? Because that was always the rub, right? How many you can move and like control.
Yeah, I think we have good plans for how to move and sort scalable qubits with trapped ions. One of the things you have to solve to scale is you have to integrate the photonics, and you have to be able to address these atoms with lasers from inside this vacuum chamber that houses the chip. And UV turns out to be very challenging for this. These photons are kind of like bullets once they're blue. And these green photons are a lot softer, so they don't damage the integrated photonics. And there's been a lot more development historically with visible wavelength and IR wavelength integrated photonics just from telecom reasons. And so I think barium will really allow us to take the next step forward in doing integrated photonics and really addressing large-scale devices with lasers.
And do you anticipate like a different layout, a different way? You know, there's that like bow tie model for how the ions are present. Do you anticipate some kind of new, more three-dimensional lattice structure or something with this kind of laser?
So I don't think the structure will change. I mean, we're
Okay.
moving towards two-dimensional geometries, just because you sort of need to have that to scale.
Hmm.
What becomes challenging is how you deliver all the lasers to address the ions in lots of different locations. And I think barium will help you there because you'll be able to sort of route the lasers on a chip, as opposed to sort of through free space trying to hit the ions as they're levitated above this trap. You can sort of in a manufacturable way route all the light to the different zones that we address the qubits with.
So this would be a form of redesign, right? It wouldn't just be swapping out ions in the current
Yeah,
machine.
that's right.
Yeah.
It's sort of been in our roadmap for a long time to move in this direction. So it's not so much of a change of direction, but it's an enabling technology to have this visible light. It'll make it much smoother moving forward.
Okay. And the goal here with the high fidelity, obviously, is going to help along things like error correction, correct?
Yeah, I think so, and I think that you know, historically the difficult thing has been the two qubit, the entangling fidelity, the two qubit gate fidelity. But as we make improvements of that, and I think these lasers with barium will allow us to make great strides in two qubit fidelity. We want to make sure that the spam fidelity doesn't become our limiting thing. So really, what this work has shown is that we can achieve the spam at a fidelity that we would be happy with long term. And so we can check it off the list and kind of redirect our focus onto these gating operations.
Okay, yeah, because there have been some things said about how many qubits of a trapped ion type would be required to create a logical qubit.
Mm-hmm.
So do you anticipate just this one change being a significant change to that, this one type of...
I think there's going to be a lot of technology that has to be developed. It'd be pretty hard to point at one thing. We've done some recent work with logical qubits. Order 10 physical qubits per logical qubit. But I do think that the fidelity helps. The fidelity affects the size of that logical qubit.
And other recent work in fidelity, it seems like there's a lot of that going on right now, right? So we're recording this right now towards the end of March, and just a week ago, Microsoft announced that they have some new advances with, they hope, with topological computing. Did you come across that, or?
I'm definitely not an expert on topological qubits. I did see that they think they measured, it was a zero mode of a Majorana particle or something like this. But yeah, I'm not an expert in that field at all.
Okay. So, and I was just wondering if you had any thoughts about how their claims will stack up to just improve fidelity in a system that already is known working, like trapped ion. If you see it.
I'm not
Okay.
certain what their fidelities would be like with that.
Okay. And also the papers that were published in Nature, did you come across those? Where they got better fidelity on silicon qubits, they were gating systems together. I don't know if your team looked at any of those too.
Yeah, I mean, we monitor all the developments. I think that other than spam, which is sort of my specialty, I don't keep track of like who's where the records are or who's winning there. But I think that I'm not super comfortable with the.
Oh yeah, no, that's fine.
Maybe
I was just curious.
Yeah,
I was asking. I didn't know if you guys keep track.
We do. I'm just not I'm not an expert on two qubit gate fidelities or anything like this.
Okay, sure. Yeah, that's fine.
Certainly not with other technologies. Yeah.
So you had mentioned earlier that this was already sort of in your timeline, this idea?
The moving towards a 2D geometry and then moving towards integrated photonics where the lasers are delivered through the traps. That's right.
Okay, so there's already potentially a system that someone behind the scenes has in mind as maybe being the first one where this would appear?
Yeah, we think about integrated photonics a lot. We think about scalability a lot. Everything we do is generally with that in mind.
Yeah, to create like a roadmap. Are you working on anything else that would affect the timeline? For example, any work in how you would have systems work together? You know, that like interconnect idea. Is there anything like that going on right now?
Yeah, I think our um, I would say that we have plans for making things scalable, but there's a lot of pieces that need to put together and a lot of technology development that needs to happen before we get to those points. But we sort of have an open mind of all these different ways and keeping scalability in mind.
Hmm. And would you say that barium 137 for now is the next qubit, or is there still work being done to see if maybe you get even better results with something else? Or
I think we keep other qubits in mind. It's important to keep an open mind, but
hmm.
they seem very promising. And our current approach is to, um, you know, where our technology development is working on 2-qubit gates and transport and figuring out how to make a scalable system out of barium, and that's what we're working on right now.
So the potential is that that's all we're going to be hearing one day. I mean, there's potential to just be barium 137, right? Ytterbium goes away.
I've been using ytterbium for a decade or so, it would be a little sad to see it completely go away. But this UV issue definitely is something that needs to be overcome, and materials in general just don't seem to like ultraviolet light. And so, just from a technology perspective, I think there's a lot of reasons why you move towards barium.
Yeah, and I realize that you're very specialized in this area, but because your company is a merger of like that pure hardware kind of side
Mm-hmm.
with Honeywell and the more software side from Cambridge, how does that like impact your day-to-day research? Do the two sides work on? Do they think ahead of the other pieces that might be involved? So, like while you're working on the new type of qubit, is there already thought being given to how that the control systems are going to be handled with software or anything like that?
Yeah, I think it's only recently happened. We haven't been merged for that long, but we've already had nice communication with the Quantinuum team that's over in the UK and
Hmm.
other parts of the world. And I think there's already sort of drawing out how can you guys help us understand what machines we should build for future. They have a lot of insight to long-term algorithms and stuff like that. And we're sort of boots on the ground, understand uh, uh, what we're building, and I think there's already starting to be some overlap there where we can learn a lot from them, and hopefully they can learn a lot about our capabilities from us.
Yeah, that's pretty exciting because I really believe that it is a full stack when it comes to quantum
Hmm.
computing. You squeeze every little bit out of across the range. So yeah, it's neat that all that new information is coming your way. Um, are there any other exciting papers maybe that we'll be seeing soon? Any other stages of this research? Um,
I certainly hope so. Like I said, we're moving forward. I think the big question is, we need to get some uh, high-fidelity 2-qubit gates out of barium, and we're actively putting a lot of effort into that. So um, shouldn't be. We'll see. Hopefully, not too long. Things move fast here, so.
and the little pieces, like this is really interesting to me, but the little pieces of technology that are needed incrementally to get these achievements to happen. um, how far out do you reach? Do you actually contact other research groups on things that maybe aren't even commercial yet, like maybe something in the lines of how a laser is controlled, or anything like that? Is there that other kind of behind the scenes synergy we're not really aware of, that kind of stuff?
I mean, yeah, we have partnerships, and we interface with some academia and some industry, right? And find overlaps and think both short term and long term in that sense. And we stage ourselves where some people are working on the immediate problems, and some are thinking about the next steps. I think that's important.
Again, thanks for doing this kind of really bleeding edge work, because we always talk about these unknowns in this industry, like what's the next unknown advance that's going to make everything just change, and increasing fidelity obviously is super important. So I'm personally really excited to see how this does when it's actually gated and running. Did you have even a remote guess at a time range where we might see these things interacting with each other, these qubits?
Everything takes some time. we're working in a faster regime now where things are years instead of decades. That's probably the best guess I could have.
Okay, so it's just still in the years range.
Yeah, it's very hard to tell. Yeah.
Yeah, because as fun as it is to just visualize scooping up the ytterbium with a little micro vacuum and then just like inserting these, it's not going to be quite that easy.
Yeah, that's right. But we've demonstrated on a system. We have barium in there, so we're moving forward as quickly as we can.
Exciting. Yeah, I'll definitely be tracking your progress. And I didn't know if there's anything else you wanted to share about what's going on at Quantinuum right now. Any other work?
No, it's very exciting. The H series systems are performing world-class systems, and hopefully we'll have the new systems online as fast as possible.
Yeah, it's been really great being able to access them. Like when Honeywell first came on, we talked about how important that is, just being able to access these systems and being able to run them per shot, that kind of model. It's really opened up a lot to the world for quantum computing. So you're all doing very important work there, so keep it up.
Thank you very much.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. Ytterbium has long been the element of choice for trapped ion systems, but the required use of ultraviolet lasers to control these ions has presented challenges. The lasers are expensive and seem to limit the fidelity obtained to 99.9%. To get to the desired 4 nines or 99.99%, a different type of laser and element would be required. Barium-133 seemed promising, but is radioactive. The team at Quantinuum tried a non-radioactive isotope, barium-137, and found that it could be controlled with affordable green lasers. Using barium-137 would not only be cheaper, but lead to increased fidelity as well. Just what type of fidelity are we measuring when we say 99.99%? Back in 2000, theoretical physicist David DiVincenzo came up with 5 criteria required for a working quantum computer, along with 2 more for quantum networking or communication. These so-called DiVincenzo criteria are as follows. 1. A scalable physical system with well-characterized qubits. 2. The ability to initialize the state of the qubits to a simple fiducial state. 3. Long relevant decoherence times. 4. A universal set of quantum gates. 5. A qubit-specific measurement capability. The last 2 for networking are 6. The ability to interconvert stationary and flying qubits. And 7, the ability to faithfully transmit flying qubits between specified locations. Numbers 2 and 5, state preparation and measurement, are called SPAM. It's this SPAM fidelity that we're measuring. Barium-137 has a nuclear spin of 3 halves. The barium-133 version has only 1 half. The extra nuclear spin creates some issues, but the team was able to overcome these leveling issues and create stable qubits with green lasers. A number of techniques are involved, including optical pumping. The stable barium-137 qubit is dark to represent 0 and lights up like a star when it's a 1. A powerful mental image to have when thinking of this system. The detectable difference between these states is measured for SPAM. Quantinuum is now working on gating multiple such qubits with each other. Achieving the high fidelity was only the first step. There will be gates for barium-137 and technologies used to improve gate fidelity over ytterbium too. To scale barium-137 gates, work will have to be done on control electronics and integrated photonics. Because some technology will still need to be developed, it's hard to say exactly how using this new ion will affect things like error correcting and the ratio of physical to logical qubits. Moving towards a 2D geometry and integrated photonics was already on the Honeywell Quantinuum roadmap. So working with barium-137 is on track with plans. It's just not clear how soon it will be before we see barium-137 as the next trapped ion qubit in production. The Honeywell-Cambridge merger has provided new insights into algorithms for the hardware team and new hardware insights for the software team. It's a full stack, with Quantinuum sharing knowledge between the two sides. Should be fascinating to see how this affects future systems. That does it for this episode. Thanks to Tony Ransford for joining to discuss qubit developments at Quantinuum. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at ConstantHacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.